Okay, this is Chemistry 2, Chapter 4, Acids, Bases, and pH. I'm going to talk about acids and bases, what they are, the idea of concentration, and the strengths of acid bases. Acid-base reactions are a specific kind of exchange reaction. The acid comes from a Latin word meaning sour or sharp. You taste lemon juice and you'd understand. Base is a chemical that reacts with an acid to form a salt. And the salt is the product of the reaction between an acid and a base. Now please note this is not table salt. This is not sodium chloride. The French apothecary Guillaume Rouelle developed the idea of a salt as a product of a reaction between an acid and a base. History there. Here's a typical acid-base reaction. Acetic acid or vinegar and sodium bicarbonate or baking soda will react to form a salt, sodium acetate, and water and carbon dioxide. So this is an acid-base reaction. The acetic acid is the acid, sodium bicarbonate is the base. Another one is hydrogen chloride and sodium hydroxide. HCl and NaOH form NaCl. In this case, it does form table salt, and water. More stuff, hydrogen cyanide, sodium hydroxide forms sodium cyanide and water. Not a good one to be working with. Svante Arrhenius was a Swedish chemist who proposed that acids produce hydrogen ions when dissolved in water and bases give hydroxide ions. So an Arrhenius acid, if you dissolve it in water, will form an anion of some sort and a proton or a hydrogen ion. An Arrhenius base has an OH group or a hydroxide, and when dissolved in water will form a cation of some sort and the hydroxide. Monoprotic acids are acids that only have one proton or one hydrogen ion. You dissolve them in water, they release only one hydrogen ion. On page 82, you can find more monoprotic acids listed in your textbook. Polyprotic acids have more than one hydrogen ion. They will release several hydrogen ions. Sulfuric acid can release 2. Carbonic acid can release 2. Phosphoric acid can release 3 hydrogen ions. Acids with 2 hydrogens sometimes are known as diprotic acids, di meaning 2. And you can see more of these on page 84 of your textbook. Arrhenius bases. Arrhenius bases release hydroxide ions. You dissolve potassium hydroxide in water and you get potassium ion and hydroxide ion. Calcium hydroxide, you get the same. You get a calcium ion, and in this case you get 2 hydroxide ions. Now this works up to a point, but when we began to get into non-aqueous systems that don't use water, we needed a broader definition, and the Brunstad-Lowry definition is the one that we can use. These were 2 chemists that developed this idea. A Brunstad-Lowry acid is a proton donor, pretty much the same way as the Arrhenius acid gave hydrogen ions. We're just saying it in different words. The Brunstad-Lowry base, on the other hand, is a proton acceptor. So sodium hydroxide can accept a proton to form water, but as we'll see in later chapters, there's more to the Brunstad-Lowry base situation. So a Brunstad-Lowry acid, such as hydrogen sulfide, a Brunstad-Lowry base as ammonia, forms the hydrogen sulfide ion, HS minus, and the ammonia ion, the ammonium ion, NH4 plus. So here we don't have hydroxide involved, but we have the base ammonia accepting a proton to form the ammonium ion. Now let's talk about the idea of concentration. Concentration is the number of units in a given volume of liquid. It might be the number of atoms, it might be the number of molecules, it might be the number of moles, the number of ions, but whatever it is, it's expressed in a given volume. High concentration means there are a large number of those units, whatever they are, in a volume of solution. A low concentration means there's a small number. Now, here's an illustration. As the solution gets more concentrated, it gets darker. It means that there are more molecules or whatever contributing to the color. The more units in solution, the darker color. Now let's be more specific. Dilute and concentrated really aren't very helpful. They don't tell us a lot. Doesn't tell us exactly how much material is in solution. It says, well, there's a lot. Yeah, there's a little. A lot to one person may not be equal to what another person by a lot. For example, the ice cream cone on the left, which has 1, 2, 3, 4, 5, 6, 7, 8 scoops of ice cream, might be a lot to a kid. The ice cream on the right with 1 scoop might be a lot to somebody that's on a diet and can't eat much ice cream because they're trying to lose weight. So a lot really doesn't say much. So we have the idea of moles, not the little animal, but molarity is the number of moles of a material per liter of solution. Now we know how to calculate moles. The grams of material divided by the molar mass gives us the number of moles. The number of 6.02 times 10 to the 23rd particles. Divide the moles by the volume, and that gives us the molarity. Well, how does this work? I have 2.4 moles of sodium bromide. I dissolve that in 1.7 liters of water. What's the concentration? Well, 2.4 moles divided by 1.7 liters gives 1.4 moles per liter, or 1.4 molar, capital M standing for molar. Now, if I had done it the other way, if I had divided 1.7 by 2.4, I'd come out with liters per mole, which doesn't make any sense. If I multiplied them, I'd have mole liters, which doesn't make any sense. So I'd know I calculated wrong. Okay, the idea of pH. Svante Arrhenius first developed the concept of pH. Now note how I write it. Lowercase p, capital H, not any of the others. And you can read pages 230 to 232 in the textbook for more detail about pH. But this basically gives you a number to indicate hydrogen ion concentration. And it's defined kind of weirdly. It's the negative log, or 1 over the log to the base 10 of the hydrogen ion concentration. So what that means, since this is a mathematical expression, as the pH increases, the hydrogen ion concentration decreases. So the higher the pH, the lower the hydrogen ion concentration. And you've got some examples in the diagram there of the pH of lemon juice, tomatoes, pure water, so forth. And here's some other examples of different solutions, egg whites, human blood, rain, so forth. Okay, now we talked about strong and weak acids. Strong acids ionize completely. Weak acids do not. Hydrogen chloride, HCl, is a strong acid. If we dissolve HCl in water, we get complete dissociation. We get all the hydrogens as hydrogen ions. We get all the chlorides as chloride ions. They are no longer hydrogen chloride molecules. They're a solution of hydrogen ions and chlorides. A weak acid, on the other hand, does not ionize completely. Acetic acid is a weak acid. Some of the hydrogens come off, some of the protons dissociate, others do not. So not all of the acetic acid molecules are ionized. Some of them are, some of them are not. Strong base, the same idea, complete ionization. Sodium hydroxide will release hydroxide ions and sodium ions when dissolved in solution. There is no more sodium hydroxide molecules. There are sodium ions and hydroxide ions. On the other hand, barium hydroxide dissociates partly. Some of the hydroxide ions will form and some of them will not. Some of the barium hydroxide molecules will ionize, others will not. So in summary, we've talked about the idea of concentration, we've defined molarity, We've told what that means. We've talked about pH, an indication of hydrogen ion concentration. Keeping in mind that the higher the pH, the bigger the pH number, actually the lower the hydrogen ion concentration there is. We've talked about strong acids and bases, where we get complete ionization of the molecules when you dissolve them in water. Weak acids and bases, you only get partial ionization. You get incomplete ionization of the acid or the base. And that's about it. I'll talk to you all later. So have a good day.